Have you ever just stared at a tiny, totally inert piece of silicon and wondered, how on earth does this little square actually think? I mean, how do we go from literal sand and metal to a machine that can render insane 3D worlds, crunch massive datasets, or, run the exact device you're watching this on right now? It honestly feels like magic. But the truth? It's really just an unbelievably clever, microscopic factory.
Welcome to today's Explainer. I am super excited to guide you through this, because today we are taking on a massive mission. We're building a brain. Well, sort of. We are stepping right inside this central processing unit, the CPU, and we're going to explore exactly how it's built from the absolute ground up. We're stripping away all the mystery to look at the raw, physical mechanics of computation. All right, let's dive right in. Here's the roadmap for our journey. First, we'll cover the basics of logic. Second, we'll assemble the core CPU components. Third, we map out the bus system network. Fourth, we'll decode computer instructions. Fifth, we'll check out the great architectural divide, RISC versus CISC. And finally, we'll push our system to the absolute limit with pipelining and overcoming hazards. So, step one, the basics of logic, the foundation of thought. Before we can build a complex processor, we really have to wrap our heads around the fact that all computer thought, every single calculation, originates from incredibly simple logical rules. At the absolute lowest level, our CPU factory floor runs on what we call combinational circuits. These are just basic logic gates wired together to make more complex circuits. And the really fascinating thing here is their sheer simplicity. Their output depends purely on their current inputs. That's it. They don't need memory to store past info. They don't even use a clock signal to keep time. They just instantly react to whatever electrical signals are right in front of them. To really see this in action, take a look at a half adder. If you want a computer to add two single-bit binary values, let's call them X and Y, you use a simple combinational circuit. Adding these bits produces a sum bit, which we'll call S, and a carry-out bit. The equation for the sum is literally just X exclusive or Y. It's just a basic logic operation. There's zero actual thinking involved here, right? It's purely hardwired logic, a physical circuit that naturally spits out the correct mathematical sum based on what you feed into it. Okay, now let's take those tiny logic gates and scale them up.
Moving to Section 2, Core CPU Components, the factory floor.
Now we're going to assemble those tiny gates into the real heavy machinery. I want you to picture the CPU as this highly efficient, totally optimized manufacturing plant. First up, we've got the Arithmetic Logic Unit, or the ALU. This is the heavy machinery. It literally does the heavy lifting for all arithmetic and logic operations. Next is the control unit, the CU. Think of the CU as the floor manager. It interprets the instructions, directs traffic, and manages the flow of data everywhere. Then we have the registers. These are kind of like high-speed tool belts worn by the workers. They're incredibly fast, tiny memory locations, holding the exact data being worked on right at that second, like the program counter, which just keeps track of exactly where we are in the process. And finally, cache memory, your L1, L2, and L3 caches. Think of this as the on-site warehouse. It's much smaller and way faster than your main RAM, and it sits right next to the processor core so you can grab data super fast. So every part of this factory has a very specific job. But a factory is useless if the stations can't actually share their materials. Which brings us to Section 3, the bus system network, moving the goods. Let's look at how these factory components actually talk to each other. If you check out the spatial map of our system, you'll see a thick line running right across the top. That's bus 1, which is basically our main conveyor belt. Over on the left, you got your general purpose registers. Moving toward the center, you see specialized registers riding this bus. The program counter, the instruction register, and the memory address and data registers, the MAR and MDR, which connect us to the outside memory. And then look over on the right. Data flows from this bus straight into register A and register B, which feed directly down to that V-shaped heavy machinery, the ALU. And the results? They loop right back up onto the bus. It is this beautifully organized, closed-loop system. Now that our factory is built and the conveyor belts are rolling, we need to actually tell the CPU what to do. On to Section 4, understanding computer instructions, the work orders. Everything a CPU does is defined by its instruction set architecture. And literally every single task boils down to 3 fundamental steps. Step 1, fetch. The processor grabs the binary code command from memory. Step 2, decode. The floor manager, the control unit, interprets that binary code using decoders to figure out exactly what needs to be done. And step 3, execute. The processor actually does the job, whether that's crunching numbers in the ALU, moving data around, or changing control flow. Fetch, decode, execute. Over and over, millions, sometimes billions of times a second. But how should we actually design those binary instructions?
Well, that leads us to one of the biggest debates in computer engineering history. Section 5, Architectures, RISC versus CISC.
Take a look at this. It shows two completely different philosophies of hardware engineering. On the left, we have CISC, or Complex Instruction Set Computer. CISC tries to do a whole lot with just a little bit of code. Its instruction set is massive and complex, the instructions are all different lengths, they take multiple clock cycles to finish, and the architecture uses fewer registers. But then on the right, we have RISC, or Reduced Instruction Set Computer. RISC takes a totally streamlined approach. The instructions are small, simple, and crucially, they are fixed length. Because they are so incredibly simple, they usually finish executing in just one single clock cycle, relying on a lot more general-purpose registers to keep data close by. It's basically the difference between giving a worker a huge, complicated manual to read versus barking out a rapid-fire series of super simple one-step commands. All right, so we've got our simple instructions, but we want to go faster, like way faster.
That brings us to Section 6, Pipelining and Overcoming Hazards, Pushing to the Limit.
Let's see what happens when we try to make this whole system run at just blistering speeds. The ultimate factory upgrade is something called pipelining. Remember those 3 steps: fetch, decode, execute. Well, in a normal, non-pipelined system, the processor fetches an instruction, waits to decode it, waits to execute it, and only then starts fetching the next one. Honestly, that's a lot of wasted time. Pipelining overlaps these tasks so they happen in parallel. While the ALU is executing instruction 1, the control unit is busy decoding instruction 2, and the system is already fetching instruction 3. Nobody is standing around waiting. And this brilliantly illustrates just how deeply this concept is baked into processor history. Take the classic 8086 microprocessor. It relied really heavily on hardwired logic, specifically to get that pipeline speed. It was actually split into 2 parts, an execution unit and a bus interface unit. The hardware circuits managed exactly a 6-byte instruction queue for prefetching. By hardwiring the 6-byte queue directly with logic gates, those simple instructions executed incredibly fast, without needing any clunky microcode. But of course, pushing limits introduces a massive villain to our speed: pipeline hazards, specifically control hazards. Think about it. If you're fetching instructions in advance, what happens when you hit a branch or a jump in the code? Suddenly, the processor has no idea what the next instruction should actually be. Because it's trying to be so fast, the pipeline just guesses. It fetches instructions before the branch is even resolved. And if it guesses wrong, well, you get pipeline stalls, which engineers call bubbles, and that's just wasted cycles. Even worse, it leads to a mandatory flush, where the CPU literally has to throw away all that prefetched work and start completely from scratch. Engineers are incredibly clever, though, and they've come up with some brilliant solutions to defeat these structural bottlenecks. First is resource duplication, basically just throwing more hardware at the problem. You create completely separate memory banks for your instructions and your data so they never block each other. Second is pipelining the resources themselves, designing the hardware to accept new inputs on literally every single clock cycle. And third is instruction scheduling. This is where the software compiler steps in and actually reorders the tasks before they even hit the CPU, seamlessly avoiding resource conflicts altogether. We have gone from simple combinational half-adders all the way up to complex parallel pipelines. It is an absolutely amazing journey of structured engineering. So, I want to leave you with this final thought. The device you are watching this on right now doesn't just have one of these pipelines. It almost certainly has massive multi-core processors doing all of this concurrently on a microscopic yet incredibly massive scale. How do you think these exact pipelining principles and hazard solutions scale up to balance workloads across multiple separate cores all at the exact same time? Think about the factory floor we just built together, and then imagine an entire city of them working in absolutely perfect synchronization. Thank you so much for joining me on this explainer, and keep questioning how the incredible technology all around you actually thinks.